Okay, today we get to do something really cool. We're going to talk about a topic that we're going to kind of start to test the waters in a topic that we'll go much further with in calculus, which is curve sketching. And we're going to talk about polynomials specifically here. There are some, when we sketch a polynomial, that's not graphing. In this day and age, when we want to graph something, we use technology to do it. So if we want a really accurate graph, we rely on technology. But a lot of times we don't need to do that. We just want to know what are the highlights, what are the interesting points on a function, and what does it basically look like. And a lot of times that's all we need. So to get there, we're going to look at a couple concepts. We're going to look at polynomial turning points and zeros of polynomials and the end behavior stuff we talked about yesterday. And we're going to put all that stuff together and do a little detective work and solve a puzzle and come up with a sketch of a polynomial. It's kind of a fun process. Real quick, before we do that, I just want to take you guys saw this yesterday. I'll just demonstrate this for you. It's kind of just cool to see it. I'm sure you talked about this. Which term most strongly predicts the end behavior of this graph? The first one, yeah, the leading term always does. If I graph this thing, you can really see this. It's kind of cool to see. So if we start off, if I'm zoomed way in on that function, that polynomial, it looks an awful lot like the linear term, doesn't it? Right? But once I start to zoom out, you can see pretty quickly that that changes, and it's not linear, and it starts to look maybe quadratic. So it starts to look maybe more like the x squared term. And if I zoom out even further, well, it starts to look like it turns again, and it looks kind of cubic almost. Okay, but if I keep going, what you're going to see is eventually this thing turns, and it starts to look, if I zoom far enough out, it starts to look exactly like the dominant term, the leading term. It doesn't look exactly like it yet, but let me zoom out a bit and you'll see. I'm zooming out pretty far here. We're getting out there. Now notice I've really stretched the y-axis so we can see this better. Really stretched it out. Well, there's a billion on the y-axis. And there's a trillion. But the x-axis is still pretty small, so we haven't seen it turn. Oh, there, it starts to turn. Okay. Okay, and we can see that when we get out to something like when x is 100,000, y is 10 to the 14th, is 100 trillion. Okay. Now look what happens when I overlap those two things. Look at that. The leading term is indistinguishable from the polynomial if you zoom out far enough. Okay, there's your proof. The leading term determines the end behavior. In fact, if you were going to look at the limiting behavior of this function as x approaches positive or negative infinity, you could literally ignore all the terms except the first term because it's going to behave exactly like that one. Okay? Give me 1 to 5 on that. Does that make sense? That's a pretty cool concept. All right, so turning points. What are turning points? They're kind of what they sound like. The turning points are the points at which a polynomial function switches direction. So in other words, an ant walking on the topography of a function, if he's walking on that two-dimensional landscape, it's where the ant is going to either switch from walking uphill to downhill or vice versa. And we always, when we talk about uphill, walking uphill or downhill, remember the ant is always going to be walking in the positive x direction. So he's walking uphill here, downhill there, uphill there. Make sense? So where he's switching directions is where we get a turning point. If the turning point is higher than any nearby point, like that one right there. Now there might be points in the distance that are higher, but relative to nearby points, that's the highest one. What do you think we call that in math? Starts with an M. we call it a maximum. Call it a relative or a local maximum. Because there could, again, it's relative or locally speaking, because there could be places out there in the distance where the ant can see higher terrain. But he is standing on a peak right there, isn't he? Okay, so it's a relative maximum. Relative maximum is always going to correspond to a peak in our topography, okay? Or topology, I should say, I guess. If the turning point is lower than any nearby point, what do you think we're going to call it? Minimum, yeah, relative or a local minimum. And that's always going to look like a valley. When we get into calculus, we'll continue to one of the things we do in calculus is we find relative extrema, relative minima and maxima, and we even can determine what their characteristics are. Are they smooth peaks and valleys, or are they sharp peaks and valleys? Okay, and then taken together, a maximum and a maximum or a minimum is an extremum, and the plural would be extrema. Okay? So turning points define the places where a function is increasing or decreasing. They're boundaries between increasing and decreasing behavior. All right, so what do you think here? If I have a polynomial of degree n, I want to know what the maximum number of turning points is, because every polynomial, not every, so polynomials, every degree polynomial, I could write a polynomial of any degree, any even degree that only has one turning point, and I could write a polynomial of any odd degree that has no turning points, that never turns. But I want to know what the maximum number of turning points is. If the degree of the polynomial is 2, show me with your arms, what's the basic shape of a degree 2 polynomial? Yeah, it's a parabola, isn't it? So how many turning points does that have? It's got 1. Yeah. Okay, what could a third degree polynomial look like? Yeah, that's one that's going to have opposite end behavior, right? So a third degree polynomial would be one that would look it could look like this. It's going to go down, it's going to go up to the right and down to the left. The only way that could happen, it could have no turning points, but the most it could have, would you agree, is 2, right? It's got to turn, if it turns once, it's got to turn again because it has to end up having opposite end behavior. Agreed? Okay. I got to pause this for just a second. Okay, so then I bet you can see a trend here pretty quickly. What about a fourth degree polynomial? What do you think the maximum number of turning points is going to be? It's going to have to be 3, isn't it? Right? And what would that one look like? That one would look, I guess, like, let's say it's positive, so it has to go up to the left and the right. If it turns once and it turns twice, it's got to turn again, doesn't it, to get back up to the correct end behavior. Everybody agree? Okay. So what's the trend here? They decrease, don't they? Right? So then, if a polynomial has degree n, it can have at most how many turning points? N minus 1. Okay, let's play a different game. This time pretend I've given you a graph of a polynomial and you're looking at it. Oops. Okay, different game. So I'm showing you a graph of a parabola, and I want you to tell me what's the smallest degree that parabola, or that graph could be, right? So what if you see that it's got 2 turning points? What's the smallest degree it could be? Show me with your fingers, everybody. Yeah, it's 3, isn't it, right? It can't be 2, could it? Can't be 2, because if the degree was 2, it couldn't have 2 turning points. It could only have 1, right? So it would be 3. Okay, you've already probably got the trend here. It's not a tough code to crack. If we see 3 turning points, what's the minimum degree that it could be? It would be 4. It could be bigger, right? But it can't be smaller than degree 4, and so on, right? So you can extrapolate there and tell me if a polynomial, if I'm looking at a graph of a polynomial and it has p turning points, then the minimum degree would have to be at least p plus 1, yeah. Okay, good. All right, that's an important clue. Okay. Here's another clue that we're going to have. So real zeros always correspond to x-intercepts. Now let's take a second and just remind ourselves, what are zeros of a function? Do you know? Zeros are the x values where what happens? Yeah, where the function, which is y, equal to y, is equal to 0, right? So that's just a quick reminder. We're going to say x values, but whatever the input variable is. Where the function, oops, didn't write function right, did I? Where the function equals 0, okay? So therefore, if that's where the function, which is y, you know, f of x and y are the same thing, if those are the x values where y is 0, doesn't it make sense that real zeros always correspond to x-intercepts, right? Okay, so that's where it crosses the x-axis. Okay, so what do you think here? Let's think about this. If I have a polynomial of degree 2, that's a parabola, right? What's the maximum number of x-intercepts that a parabola could have? Show me with your fingers. Yeah, wouldn't it be 2, right? Because it only turns once, right? Good, so it would be 2. What if it's cubic? Well, if it's cubic, we said that's one that looks like kind of could have that shape. If that's the x-axis, wouldn't it have 3, right? Okay, this is a pretty easy trend. If it's a 4th degree polynomial, what's the biggest number of x-intercepts it could have? 4, and so on. And so a polynomial of degree n can have at most how many x-intercepts? Of degree n can have at most n x-intercepts, exactly. Okay? So let's turn that around then, and this is pretty simple. If I show you a graph of a parabola that has 2 x-intercepts, we know that parabola has to be at least degree 2. Yeah, right? Could be bigger, but it can't be smaller degree. If we see a graph with 3 x-intercepts, the degree of the polynomial has to be at least 3. Can't be smaller, and so on. Okay? So if a polynomial with Sx intercepts has a minimum degree of S. Okay? So now we get to, this is where it gets to be a little more fun. Now we get to try to determine what the minimum degree of some of these polynomials are. Okay? So what are the things we know here? Well, first of all, this isn't really related to that last question, but when we sketch polynomials, it's going to be important. Tell me real quick, is the leading coefficient positive or negative here? It's positive, isn't it, right? Because what kind of end behavior is that? Positive, even or odd? Odd, yeah, good. Okay, so we know it's positive leading coefficient. We know it's odd end behavior, right? Okay, I'm going to write that too. Odd end behavior. So we know n, the degree of this thing has to be odd. What's the minimum degree? Well, let's figure this out. The number of turning points, how many turning points do you see in this function? Tell me with your fingers. 2, yeah. Okay, so if we have 2 turning points, that predicts a minimum degree of what? 3, yeah. You have to have at least one higher degree than the number of turning points, right? Okay, how many x-intercepts do you see? 1. Right there. Well, that clue predicts a minimum degree of what? 1. And we know that it's odd. So what's the answer? What is the minimum degree then? If you add all 3 of those clues together, what's the minimum degree? It's got to be 3, right? Doesn't that make sense? If one clue is telling us the minimum degree is 3, and another one is telling us the minimum degree is 1, well then it has to be 3, right? Does that make sense? Okay. Okay, give me thumbs on that. That make sense, everybody? Okay. Let's try it again here. Positive or negative leading coefficient? Negative. It's negative even behavior, isn't it? Okay. How many turning points do we have? Show me the fingers here. Looks like 3. Good. 3 turning points, which predicts a minimum degree of 4. How many x-intercepts do you see? 3. Yeah, 3. I see 1 there, and 1 there. That predicts a minimum degree of 3, but the end behavior tells us that n is even or odd? Even. Take those 3 clues and tell me what's the minimum degree. 4. Yeah. Got it. Okay. For this function, f of x, real quick, what's the maximum number of real zeros it can have? You can just say it, everybody. 8, right? Good. Okay, because that's the degree. What's the maximum number of x-intercepts? 8. They're the same question, aren't they? X-intercepts and real zeros are the same thing. And what's the maximum number of turning points? 7. Yeah. 1 less. All right, so now this is really cool. This is an honors topic here. This is really cool stuff. So the multiplicity of a 0 is equal to the number of times its corresponding factor occurs. Okay? So I'm not expecting you to do a bunch of factoring in this assignment. Factoring is something we're going to review, and you'll do a lot of factoring, but we're not quite there yet. So we'll kind of limp through a couple, you can probably, as a group, we can do this factoring. I think it'll be fine. The problems you get on the assignment will all be factored for you to begin with. Okay, later on, you can see, though, by factoring polynomials, putting them into factored forms, we're going to be able to use this trick that we're learning today, later on in the class. Okay, so we've got this function, this cubic polynomial. Let's put this into factored form first. Okay, remember, when we're factoring polynomials, what's the first thing we always try to do when we're factoring? I know you guys have done this in a long time. We always want to factor out the GCF. So is there something I can undistribute from each term? X I could, right? Everybody agree? I could undistribute an x. So I get the GCF, x. What's left behind when I undistribute the x? If I undistribute the x, if I'm factoring it out. Okay, good. So x squared minus 6x plus 9. Okay, good. Okay, now we want to see if we can factor that trinomial. Okay, maybe we can, maybe we can't. And we'll go, again, we'll review this stuff later. Real quick though, what would have, if I can, what would have to go there and there? X's, right? And I've just got to see if I can find magic numbers that would work for me to FOIL this out and get that trinomial. Do you remember the recipe for that? The magic numbers would have to multiply to what number? They have to multiply to 9, to the constant, and add to -6. Yeah. So what two numbers multiply to +9 and add to -6? -3 and -3, right? Well, how could I write x minus 3 times x minus 3? X minus 3 squared. Good. So then we end up with f of x is equal to x times the quantity x minus 3 squared. Okay. So now what are the zeros of this function? Well, the zeros would just be the places where that function is equal to 0. And this is what factoring allows us to do. And again, we'll review all this stuff soon. But if I were to set this function equal to 0, what's the only way that I can multiply two things together and get 0 as a result? I have to multiply by 0, exactly, right. So I just need to find the zeros of each of those factors are going to be the places where that product equals 0, right? I want to find the values of x that would make each one of those individual factors equal to 0 so that I could multiply to get 0. Okay, what's the 0 of the red factor? What's the value of x that makes it 0? 0. Okay. What's the value of x that makes the blue factor 0? 3. Okay, so those are my zeros. X equals 0. We would say that that one has multiplicity multiplicity 1 because the power of x is 1. It only shows up once. And x equals 3 with multiplicity 2 because it shows up twice. Why is that a big deal? Because the multiplicity determines what the x-intercepts look like. This is really cool. Okay? So if we were to graph this thing, what we would see is, okay, let's do this. Let's graph it. So we know some clues here. We can kind of figure this out on our own. We know we have x-intercepts at 0 and 3. And what's the end behavior of this polynomial going to be? Positive odd, right? So that's going to rise to the right and fall to the left, agreed? Okay, there's two ways that that could potentially happen. Does this make sense? Like one way that could happen is if I cut through that x-intercept and bounce off that one to go back down. But it has to go down to the left and up to the right. The other possibility would be if it bounced off of this guy and cut through that guy. But those are different looking graphs. How do we know which one it is? Because of the multiplicities. Because of the multiplicities. Here's the rule. If the multiplicity of a 0 and a factor is odd, then it's always going to cut through the x-axis. That's what the x-intercept does. If the multiplicity of a factor and a 0 is even, it's always going to bounce off of the x-axis. So which one is it then? Orange or green? It's going to be green, isn't it? Whoops. No, orange, isn't it? Orange, yeah, because it's got to bounce on the multiplicity 2 and cut on the multiplicity 1. Agreed? Okay. Oops, so let's graph that one again. So it's got to do, that. Okay? Now what's even cooler, and this is a higher concept, but you guys, I want you to be aware of this. This is really cool. Zeros always act like their parent functions. Okay, I'll show you what I mean by that. Let's take this example. We've got the function already in factored form. So what are the zeros of this function? What's the first zero going from left to right? Everybody agree? -7? Okay. So I'm going to get this guy, the zero of this one. We get x equals -7. Okay. What's the multiplicity of that zero? Show me with your fingers. What's the multiplicity of that zero? 2. Good, because that factor squared. So what's the effect going to be? What's going to happen with the x-intercept? Going to bounce or cut? It's going to bounce. It's going to bounce at -7. Okay, what's going to be the what's going to be the zero of that factor? All I have to do is set it equal to 0 and solve. So what's x? If 2x plus 1 equals 0, x equals -1/2. Yep. You guys said it and I didn't hear you maybe. Okay, so we have 0 at -1/2. What's the multiplicity? 1. So what's it going to do? It's going to cut. And I could even go further. It's going to cut like a line. Because the power is 1, that's a linear polynomial, so it's going to cut through just like a line would cut through. Okay, this is what's really cool. What about this last one? What's the zero of that last factor? Yeah, it's 4. What's its multiplicity? 3. So what's it going to do? You're going to cut or bounce? Going to cut. What's it going to cut like? It's going to cut like a cubic. It's not going to cut like a line. It's going to cut like a cubic where it does that. Okay? I'll show you. This is really cool. You can see this. Oh, geez. Okay, there's that graph. Okay, what do we see? At -7, sure enough, bounces like a parabola, right? At -1/2, it cuts like a line. At +4, it cuts like a cubic. And then we know what the end behavior is, so that's all we need. Those are all the clues we need to get the basic shape of this parabola, right? Because we know it has, if I were to multiply all that out, wouldn't I end up getting, let's see, I'm going to end up getting an x² x to the 6th positive. I'm going to end up getting some positive coefficient times x to the 6th, so I know it's got to do that, right? Okay. Wonder, can I zoom out a little bit? Wow. That's pretty good right there. I'll put that in our notes. Okay. What about this guy? Okay, again, this is one where we'd have to factor it. And I'm not going to have you, I don't think I have you do any factoring on the assignment. I said I didn't, but I forgot to look. I don't think I did. This is an easy one to factor, though. Squared. Okay, good. So and if I do that, what's left behind? Minus 2x minus 8. Okay, good. Okay. Do that probably. So what does that factor into? I know I'm going to get an x and an x, right? What numbers multiply to negative 8 and add to negative 2? Minus 4 and positive 2. I think I got those colors backwards, darn it. I'm going to do this. I'm going to do plus 2 minus 4. I think that'll match up. So what are my zeros? What's the zero of the red factor? 0. Okay. So what's he going to do? Going to bounce. 0. Negative 2. What's, oops, I got them backwards. I had it right the first time. I guess I got the colors backwards. So the green 0 is 4. The multiplicity is 1, so it cuts like a line. The blue 0 is negative 2, multiplicity 1, so it also cuts like a line. And we could graph that. Yeah, that's all it takes. Those are all the clues you need to sketch this thing. Okay, how about this one? How could I, this is the last one we'll do. A polynomial function, I'm telling you this, it has a 0 at negative 6 with a multiplicity of 2, and it has a 0 at x equals 2 with a multiplicity of 1. I want you to build the simplest polynomial function in standard form that would have those characteristics. Pieces here. If it has a 0 at negative 6 with a multiplicity of 2, okay, let's work backwards. X equals negative 6 is my 0. How could I turn that into a factor? What's the factor that goes with that produces that 0? In other words, what would I set equal to 0? What factor could I set equal to 0 to get that? Let's do this very generally. X minus c is a factor, then x equals blank is a 0. C, right? Because if I said x minus c equal to 0 and solve, I get x equals c. Work backwards, right? If c is a 0, then x minus c must be the factor that goes with it. Okay, we'll use that trick. If negative 6 is the 0, then x minus negative 6, which is the same as x plus 6, is the factor. Everybody see that? Okay, so that gives me the factor, whoops, that gives me the factor x plus 6, but the multiplicity is 2, so it's. All right, how about this one? We have a 0 of 2 with a multiplicity of 1. So the 0 is 2. What's the factor that goes with that then? X minus 2. Boy, that doesn't very much look like a 6, does it? Oops. Let's fix that. Okay, and so f of x, the simplest polynomial I can build, is multiply them out, right? That's a Good place. Did that one. I showed you that. Oh. Well, I guess we could start this. So there's our function. What's the graph's end behavior going to be? In other words, if I multiplied that whole thing out, what would the leading term be? Mm-hmm. 2x to the fourth, everybody agree? Give me 1 to 5 on that. Everybody good with that? If I FOILed the whole thing out. It would be a mess, but the first term would be easy to calculate. I'm going to get an x squared as my biggest term. If I distribute that to the biggest term here, I'm going to get an x to the fourth, and then I've got a 2 to multiply through, right? I'm going to get a bunch of other stuff, but I know I'm getting 2x to the fourth plus other stuff. But that's my leading term. Behavior then. Yeah, positive even, so it rises. So it's got to be third option, right? Okay. X-intercepts. What's that x? 2. What's that x-intercept? Okay, well, how about that one? That one's a little bit tougher. What if we take x squared? Again, this is stuff that I'm kind of jumping ahead a little bit. If I set that equal to 0, what do we get? Equals 9, right? So what's x equal to? 3 or negative 3. And we'll talk about that. We'll talk about why that is. We're going to come back and review that. So x equals plus or minus 3. So I get a total of, again, I'm jumping ahead. We'll review all this stuff, right? The x-intercepts are 3 of them. So where does the graph cut through the x-axis? At which x-intercepts? And maybe a better way to do this, you know what? Okay, yeah, we better wrap this up. But that factors, doesn't it? X squared plus 0x minus 9. I have to find two numbers that multiply to negative 9 and add to 0. What are they? 3 and negative 3. There you go. X minus 3 and x plus 3. So now that gives us, if we factored it like that, right? Now we end up with f of x equals 2 times x minus 2 squared times x. Is that easier to see where the x-intercepts are? That gives us 3 x-intercepts. Okay, what values of x does it cut through the x-axis at? 3 and negative 3, yep. Because those are the multiplicity 1. Where does it touch and bounce? At 2, right? Because that has degree 2. Okay? Perfect. Okay, that's a good place to stop.